Well, good morning. We will continue with the portion on nozzle. What we do today is we will find out what is the effect of area ratio. We will define area ratio. We will also find out how the nozzle operates at different altitudes and look at some typical results. But before doing that, let us quickly recap where we were so that we can connect it with what we are going to do today. All what we told in the last class was a nozzle, if we need to have a high jet velocity, needs to have a convergent, maybe it should have a throat for which Mach number is equal to 1, and then I should have a divergent. We were very clear about the throat. We said it is the place where the velocity is sonic, that means the throat velocity is the sonic velocity, maybe Vt is equal to At. We also told ourselves any disturbance here, suppose I stand on the nozzle here and make a loud noise, or I do any disturbance, this disturbance cannot enter the convergent and therefore the chamber over here. The reason being the velocity here is equal to the velocity of sound in the throat and is greater than the sound velocity in the divergent, and any disturbance which generates downstream cannot travel here because the speed here itself is sonic, and therefore we told ourselves any disturbance downstream of the throat cannot enter the chamber, and therefore the sonic throat essentially decouples the convergent and the chamber from the downstream portion. This is because the disturbances travel at the sound speed. Second thing, we also told that the throat is choked. In other words, we told ourselves that for the given mass flow rate I can have a maximum velocity which corresponds to sound speed at the throat, and if I have higher pressure or if I suck it at a lower pressure, I cannot exceed this condition. That means the throat always will have Mach number equal to 1, or the velocity here should be the sound speed. I think these definitions are important. We also derived an expression for the jet velocity at the exit, which we derived as Vj as equal to 2 gamma divided by gamma minus 1. We will write in terms of the specific gas constant R into the temperature within this chamber into, we had something like the expansion 1 minus the exit pressure, that is the pressure at the exit over here, divided by the chamber pressure here, P of the chamber over here, and this Pe by Pc to the power gamma minus 1 by gamma, and this was under root. And this we did not even consider the convergent divergent shape. We just said that if the chamber pressure is Pc, if the exit pressure is Pa, then you have the pressure ratio coming, this is the temperature in the chamber, and this is how we derived the expression for Mj, which was so many meters per second. Is it all right? And what we started with a vent, we derived this velocity, and then to look at the shape of the vent, it was necessary for us to have a convergent followed by the divergent, such that if I were to now plot the velocity of the gases as a function of the length of the nozzle, mind you, along the length of the nozzle initially I have a converging shape, then I have a throat, then I have the diverging shape. This is where I get the sonic velocity, and therefore the velocity will keep increasing along the nozzle. The moment I have at the throat the velocity less than sonic, the velocity builds up and thereafter the velocity falls. Therefore, the necessity to have Mach number 1 at the throat was essential, right. I think this we must remember all the time. Having said that, now in today's class we will try to see, instead of mentioning that the exit pressure is Pe, now after all I have to realize a nozzle, can I put it in terms of a number, let us say the area ratio at the exit will be Ae, and therefore what must be the area ratio Ae such that the nozzle will give me the required velocity. and that is what I want to do today. Let me repeat again. See, when I realize a hardware, I do not know the value of PE. All what I know is I must have a configuration like this, I must know a diameter over here, I must also have the diameter at the exit, or rather the exit area ratio. Therefore, it becomes essential for me to define something like area ratio of a nozzle. To be able to give me the value of PE such that I can get the jet velocity, or rather I want to know the configuration. Let us put it this way, I have a convergent, I have the throat, I have the divergent, I want to know what will be my exit area ratio such that I can get the Vj whatever I want. I want to find out the expression for the jet velocity in terms of a diameter or an area ratio rather than put it in terms of the value of the pressure at the exit, which we called as PE. To be able to do that, we tell ourselves, well, I am looking at the exit area, I would like to define the area at the throat, because I know that at the throat the Mach number is always equal to 1. Therefore, I can define it as a critical or a particular area for reference, and I call the nozzle area ratio as equal to the exit area divided by the area at the throat. This is by definition. In fact, initially all of us tend to think, if I have to define something like an area ratio, maybe I should think in terms of the area of the chamber over here and relate it to the area at the exit, but whatever be the area here, the reference is the throat, because that is where the velocity is always equal to the sound speed, or Mach number is 1. Therefore, we define the nozzle area ratio as the exit area divided by the throat area, and it is denoted by epsilon, and epsilon is equal to AE by AT. Is it okay? Having said that area ratio is AE by AT, I want to derive an expression how the area ratio will affect the jet velocity, or how would a performance of a nozzle be linked to the exit area ratio. Let me repeat the problem such that it becomes a little more clear. Supposing I have a small rocket, let us say, I bring it to the throat Mach number 1, I could have a small area ratio, or I could also have a same rocket in which, now I again draw this one over here, I could have a very large area ratio. And how do I find out compare the performance of an area ratio which is AE1 with area ratio AE2, and if the throat area is the same in the two cases AE by AT2, I have area ratio 1 is equal to AE1 by AT1. In the second case, I have area ratio is equal to AE2 by AT2. I want to compare which one gives me a higher velocity. I want to compare these two nozzles, and therefore we define area ratio as exit area divided by the throat area. The reason being, I could have had a larger chamber, something like this, with a much larger chamber, but still even for a larger chamber the throat area would be the same for a given condition, namely Vt is equal to At over here. I think we must keep this in mind. Area ratio is always defined with respect to the throat, that is exit area divided by the throat area. I want to determine it. Let us go ahead and try to write an expression. Therefore, I am interested in finding the value of AE by AT for a nozzle. And how do I do it? I just look at the continuity. I look at the mass which is coming over here, mass which is passing through the throat, mass which is passing through the exit, and I write m dot is equal to the mass which is passing through the throat rho t into the velocity at the throat is equal to the area at the exit, rho at the exit, v at the exit. Is it all right? If anybody has a question, please, I think this is the time to take it up. Therefore, we find that I need the condition at the throat, namely the rho t at the throat I need to be able to find out. I also need rho e. I know V is nothing but the velocity with which it is exiting. This will be equal to the Vj, which I have already derived. Therefore, I need to find the conditions at the throat. Therefore, let us first spend a couple of minutes on deriving the expression for the conditions at the throat, which are so critical to a nozzle. Let me again repeat, the condition at the throat will specify the mass flow rate because it is choked over here. I will come back to this later, but let us first find out what are the density, pressure and temperature at the throat. We say the throat is defined by density at the throat rho t, Vt, pressure at the throat is Pt, temperature at the throat is Tt. That means subscript T denotes the throat condition. And how did we define the pressure conditions or the chamber conditions? Rho c, capital C over here, velocity in the chamber which we said was equal to 0, pressure at the chamber, temperature in the chamber. At the exit, rho exit, V exit which is equal to the jet velocity at the exit, P at the exit, T at the exit. Well, these are the variables what we have. I want us to find out the value of rho t as a function of rho c, maybe Pt as a function of Pc and Tt as a function of Tc. Therefore, we again just look at the conditions, we tell ourselves again we are deriving the same expression, we are interested in the condition at the throat over here. The conditions are given by subscript T over here for rho, V, T and all that. This is the chamber condition. We treat this as a control volume, or rather now we are considering our attention is only in this small region which I show hatched over here. Gas enters at a pressure Pc at velocity 0 at a temperature Tc. At the throat it leaves at a condition rho t at a velocity equal to the sound velocity because it is choked at a pressure Pt and at a temperature Tt. So, let us write the expression for this control volume. Let us again assume adiabatic condition, and therefore, we can write the enthalpy entering is Hc plus kinetic energy 0 is equal to H at the throat plus I have Vt squared divided by 2 kinetic energy. We must be able to write, this is a steady flow energy equation, same mass flow is there, enthalpy comes over here corresponding to this, initial kinetic energy is 0, exit at the throat the enthalpy is Ht and Vt squared by 2 is the, or Vt is the velocity at the throat, kinetic energy at the throat is Vt squared by 2. Okay. Now, let us simplify this equation. We get from this equation Vt squared divided by 2 is equal to Hc minus Ht, and what is the difference in enthalpy is equal to Cp Tc minus Tt, and therefore, what is Tc minus Tc? Tc minus Tt is equal to Vt square divided by 2 Cp. Now, please just if there is anything, please let me know. What is the value of Cp in terms of gamma? Vt square divided by 2 gamma divided by gamma minus 1 into R. How did this come? We have derived it in the earlier class. Cp minus Cv is R, Cp by Cv is gamma, and therefore, Cp is equal to gamma by gamma minus 1 into R, and therefore, I can write this expression as equal to gamma minus 1 divided by 2 into Vt square divided by, what is it I get? Gamma R. And therefore, I can now write the value of Tc I take Tt on the other side is equal to Tt into what I get now 1 plus gamma minus 1 divided by 2 into I now write Vt square divided by gamma r into Tt. What did I do? I have taken Tt at the bottom and therefore I have gamma minus 1 Vt squared by gamma r here. Is there some 2 missing? No, it is all right. And now I know gamma RT is the sound speed, or gamma r into Tt is the sound speed at the throat. Vt is also equal to the sound speed at the throat. Therefore, this is the Mach number square, and I get 1 plus gamma minus 1 by 2 into Mach number square. Mach number is 1, and therefore I get the value of Tt as equal to 1 plus gamma minus 1 divided by 2, or this gives me the value of the temperature at the throat as a function of the chamber temperature as equal to Tt by Tc is equal to, now this becomes gamma plus 1 by 2, I take it the other side, so T becomes 2 plus gamma plus 1. Therefore, what is it we find? That the temperature at the throat is approximately 1 over 1.2 times that in the chamber, or rather if the chamber temperature is something like 2000, then it will be something like 1300 or 1500 degrees centigrade. In other words, if gamma is equal to 1.4, the value of Tt by Tc is equal to 1 over 1.2, or depending on the temperature here, if the chamber temperature is 2000, the value at throat is equal to 2000 divided by 1.2, which is equal to maybe 180, maybe something like 1600 and maybe 50 or something like this. Therefore, the temperature falls at the throat and it is around, depending on the value of gamma, you get a smaller value, right. Now, what will be the value of Pt by Pc? We have derived the expression in the last but one class. What did we tell? It is equal to Tt by Tc to the power gamma by gamma minus 1. Please look back, let's check it. And how did we get this? We had P by rho is equal to P by rho is a constant, P by rho t is a constant. Solving for this, we got this particular expression. In fact, you will remember in the expression for Vj, what we had, if you remember, we had the expression 1 minus P by Pc to the power gamma minus 1 by gamma. How did it come? This was essentially Te by Tc, and when we converted it in terms of the pressure ratio. What is the value of rho t by rho c? 1 over gamma this, that is equal to 2 over gamma plus 1 to the power 1 over gamma minus 1, and this maybe I should have written here as 2 over gamma plus 1 to the power gamma divided by gamma minus 1. What is it we have derived? We derived the conditions at the throat, namely the value of the temperature at the throat, the value of pressure at the throat, the value of density at the throat as a function of the conditions in the chamber pressure, which is known to us, which is what we are given with, maybe that is the chamber condition. I want us to go back and apply these three relations over here. We know the density at the throat, maybe I have to find out the density at the exit and find out the value of the exit area ratio as a function of the exit pressure, or exit pressure as a function of area ratio I am interested in. Therefore, I hope by now we know how to evaluate the conditions at the throat of a nozzle, and all what we have learned so far is, if I have a throat coming from a chamber pressure Pc, temperature Tc, density Tc, I know how to find out the conditions of Pt, Tt and rho t. Agreed? Now, let us go back and solve that equation. namely we said area at the throat, velocity at the throat into the density at the throat is equal to area at the exit, velocity at the exit, rho at the exit, or rather from this I get the area ratio AE by AT is equal to Vt into rho t divided by Ve into rho e. Is it all right? I want to substitute the values. I know the value of rho t in terms of rho c, therefore I say this is equal to 2 over gamma plus 1 divided by 1 over gamma minus 1. I take this particular expression rho t by rho c is equal to 2 over gamma plus 1 1 over gamma minus 1, and then I now have the value of rho t is now into rho c into Vt, I still keep it as Vt, and now I know that V is equal to Vj. What is the value of Vj? 2 gamma, gamma minus 1 RTC, 2 gamma RTC gamma minus 1 into 1 minus Pe by Pc to the power gamma minus 1 by gamma under root into the value of rho e. Okay. Now I want to somehow get rid of rho e, also Vt. Vt I can write in terms of the sound speed, and this is equal to At, and therefore here I can write it as equal to under root gamma r temperature at the throat. Please be let's be very careful, because these are all simple algebraic expressions. We are substituting one into the other, and in the process we are also learning how the properties are varying. Let's solve that equation further. Therefore, the area ratio epsilon is given by, let us write it down, 2 over gamma plus 1 to the power 1 over gamma minus 1 into rho c. Rho c I can write it as Pc divided by RTC. P is equal to rho RT, P by rho is equal to RT, therefore rho is equal to P by RT. We have made use of the ideal gas equation, P is equal to rho RT, and therefore rho is equal to P by RT, Pc by RTC. And now I have another value gamma r. Now let's strike off some of the numbers here. Here I have under root gamma, under root gamma, under root r, under root r. Therefore now I get a value which in the denominator would be we'll take Tc outside, 2 over gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma under root. Now I have under root Tt here, I have under root Tc here. Is it Tc? I am sorry. Is it okay? 2 over gamma plus 1 P by R Tc into under root Tt on top, gamma r get cancelled, therefore I had 2 by gamma minus 1 into this term Tc over there. I want to further simplify it. We had derived an expression for area ratio as given by the above expression. We would like to simplify the expression by expressing as ratio of pressure, as ratio of temperature, so that we can write it as a function of the Pc and Pe alone. For this purpose, let us take a look at what we can write rho e as. Maybe I can write the value of rho e in terms of the pressure at the exit as saying pressure at the exit divided by rho e is equal to PVE is equal to R into TE. Therefore, that is pressure divided by density is equal to specific gas constant into the temperature at the exit. I simplify this expression to give me rho e as equal to PE divided by R TE. Therefore, now I can substitute the value of rho e as PE divided by RTE, so that now I get an expression for PC by PE. This is one. Second is, I can also make some changes for the value of TT, that is the temperature at the throat, and we had seen earlier that the temperature at the throat divided by the temperature at the chamber, at the throat the Mach number is unity, and therefore, this is equal to 1 plus gamma minus 1 by 2 into 1 square, or this is equal to gamma plus 1 divided by 2. Well, there is some problem here. The temperature at the throat reduces with respect to the chamber is stagnation. Therefore, this expression should really have been something like Tc, that is the temperature in the chamber, divided by the temperature at the throat. Therefore, now I can write the temperature at the throat is equal to 2 over gamma plus 1 into the temperature of the chamber. Now, these two things, namely the value of temperature at the throat in terms of the chamber temperature and the exit gas density in terms of PE by RTE, I substitute it in this particular expression, and now we therefore get the area ratio epsilon as equal to 2 over the same things I write again, gamma plus 1 divided by 1 over gamma minus 1, and now PC divided by RTC, and now I get the value of TT divided by TC, but my value of TC is therefore I write it as 1 over under root TC, which is over here. Under root TT I can write as 2 over gamma plus 1 divided by half into under root TC. This is where I have written this, and 1 over rho e, and 1 over rho e is equal to RTE by PE, and this is divided by the same value what I had here, namely 2 over gamma plus 1 under root 2 over gamma plus 1, gamma minus 1 I am sorry, into 1 minus PE by PC to the power gamma minus 1 by gamma, close bracket over here. Here also the bracket should have been closed here. Now, let's simplify this. You find that you have under root TC cancels, and now if I were to put it in terms of TE by TC, in terms of PC by PE, I will get an expression which gives me epsilon is equal to, or the area ratio is equal to 2 over gamma plus 1 divided by 1 over gamma minus 1 to the power. Now, I have PC here, I have PE here, let us write it as PC by PE, and now if I take R also cancels over here. Therefore, now I write T is left over here, that is the exit temperature, and there is nothing else here. Let's write that down. I have the value of T over here, and I have taken PE inside, and here I have TC over here, and this divided by, of course I need to take 2 over gamma plus 1, this is 2 over gamma minus gamma plus 1, 1 over gamma minus 1, and this I take 2 over gamma plus 1 half into under root of the same denominator which comes over here, 2 over gamma minus 1 into 1 minus P by Pc to the power gamma minus 1 by gamma and close bracket here. Now, immediately I see that 2 over gamma plus 1, 2 and 2 gets cancelled over here, gamma plus 1 comes on top, and therefore, now I can write the denominator as equal to gamma plus 1 divided by gamma minus 1 into 1 minus Pe by Pc to the power gamma minus 1 by gamma close bracket over here. And now let's simplify the numerator. I get 2 over gamma plus 1 divided by 1 over gamma minus 1, and now can I express these things together? Can I express Te by Tc in terms of Pc by Pe? See, we have been doing this. We always said Te by Tc using the isentropic expansion. We can always write it as Te divided by Tc is equal to Pc divided by Pe to the power gamma minus 1 by gamma. You will recall we have done this several times, and therefore, if now I say Pc by Pe and I add this together, I will get an expression in terms of, let us put it Pc by Pe, and now I have the value over here Pc by Pe, and now I have Te by Tc, Te by Tc which should go as Pe, mind you in the same order, Pe by Pc, and therefore I will get Pc by Pe into the value of 1 minus gamma minus 1 divided by gamma, which is equal to Pc by Pe to the power 1 over gamma, because 1 minus 1 plus 1 over gamma, it becomes 1 over gamma, and therefore I can write this as equal to Pc by Pe to the power 1 over gamma, and therefore my net expression now becomes 2 over gamma plus 1 to the power 1 over gamma minus 1, Pc by Pe to the power 1 over gamma divided by gamma plus 1 divided by gamma minus 1 into 1 minus Pe by Pc gamma minus 1. What does this expression tell us? This expression tells us that the area ratio of a nozzle can be given by this particular expression, and as the chamber pressure increases, the area ratio increases, or rather as the ratio of Pc by Pe increases, the area ratio increases, which can come about either by increasing the chamber pressure or by decreasing the exit pressure. If I have a very low value of exit pressure, my pressure ratio is larger and I require a larger area ratio nozzle. Of course, gamma also plays a role, but a secondary role, but the main aspect of area ratio comes from the change, from the variations in the value of the chamber pressure to the exit pressure. What does this expression tell us? Now we just look at this expression, we find that area ratio which is dimensionless, which is equal to AE by AT, increases as the value of PE by PC increases. In other words, as PC by PE increases, we get the value. No, let's be very clear. I think somewhere some goofing has taken place. Have we taken? Yes, rho C by rho E. We get the value of PC. Yes, when the chamber pressure is high, when the exit pressure is smaller, I have the larger area ratio, and this being much stronger, the area ratio increases as the value of PE by PC. No, I should have put PC by PE increases. I think we must remember this. I have confused this. The reason being, when I talk in terms of chamber pressure, either the chamber pressure can be very high or the exit pressure can be very small. Therefore, when I write the value of PE by PC, I mean a small value of ambient pressure and a somewhat large value of PC, or the same thing I can have a rocket at a very high pressure and I can have the PE to be reasonable, and still I get a large value of PC by PE or a small value of PE by PC. I think in the plots which we plotted, in which case you will recall we had a plot of Vj and we plotted it as a function of PE by PC. What we told was, when the value of PE by PC is small, I get a large value of Vj. Please look back, yes. And therefore, what we find from this expression is, I get a large value of area ratio when my pressure ratio is small. Let us take a look at some of the values maybe which I have plotted in the slides over here. See, I quickly run through whatever is given here. Area ratio is defined by the value of AE by AT, and this is the expression we had got. We had the jet velocity VE given by 2 gamma minus 1 gamma minus 1 RTC 1 minus PE by PC, and thereafter we wrote the area ratio in terms of these parameters and got this particular value, which worked out to be 2 over gamma plus 1, 1 over gamma minus 1, PC by PE 1 over gamma. We should have had gamma, yeah, I think we have swallowed 1 over gamma plus 1 somewhere. We should have got the expression as gamma plus 1 into 1 minus PE by PC. Please check it, somewhere you would have left out something, and when I plot this number, I get the area ratio as a function of PC by PE. As PC by PE increases, the area ratio increases, and in fact as the gamma decreases from gamma of 1.4 to 1.1, I find a larger area ratio is required to give me the same value of PC by PE. I put it for larger value of pressure ratio. Here again the value is PC by PE as a function of the area ratio. You find that as gamma decreases, I need a larger value of the area ratio. In other words, what it tells me is, if my gases have a smaller value of gamma, then I need a larger area ratio to give me the same value of pressure ratio. I think this is all about area ratio, but please go and check for this expression and correct it. What is it we have done so far? We found out the value of the area ratio and related it to the value of the chamber pressure divided by the exit pressure over here, PE. Now, in general, area ratio of most of the nozzles will be between, let us say, 15 to 400. This is the type of area ratios what we employ. If we were to look at the expression for area ratio, you find that when P becomes 0, I need area ratio which is something like infinity. I cannot have infinity because I cannot afford to have a rocket motor which gives me a very large value. I cannot keep on extending because the mass of my rocket will keep on increasing. Therefore, the general practice is to have area ratios between 15 and 400, 15 for those rockets which operate within the atmosphere or within near to the earth, and 400 or values around this for rockets which operate in the vacuum regions. Therefore, the question which now comes is, if I give supposing I have a rocket nozzle, let's have some clarity on what I propose to do now. Suppose I have a rocket nozzle which, let us say, has a small value of AE by AT. This is the value, I say epsilon 1, which is equal to AE1 divided by AT1. For the same condition of the throat, I also have another rocket which has a larger area ratio, let us say AE2 for the same value of, let us say, AT1. That means I have epsilon 2 is equal to AE2 divided by AT1. Now the thing what I want to do, what I want to describe is, suppose the chamber pressure is the same in both the cases, what I am going to get here is a smaller value of PE2, and here I get PE1, or rather I get the value of PE1 will be greater than PE2, right. I have a smaller nozzle, it expands to a higher value of pressure, I expand it still further, therefore the value of PE2 is less than PE1. Now if we have rockets of different area ratios, and we also know, maybe I plot the value of pressure as a function of altitude, pressure keeps decreasing as altitude increases. At ground level I have a pressure of, let us say 1 atmosphere or 10 to the power 5 Pascal. As I keep increasing in altitude, it decreases till the time we leave the atmosphere, let us say around 50 or 40 kilometers, the pressure has gone down to a very small value, and when I go to geosynchronous altitudes it is almost perfect vacuum. Therefore the ambient pressure also plays a role. Let us assume that in this case PE1 is there, I have the ambient pressure is PA over here, the same ambient pressure is over here. Therefore let me plot it a little on a plot now. All what I am trying to do is, I am trying to plot the pressure and the pressure variation along the nozzle. In the first case it starts with a value of PC, comes down to a value of PE1. In the second case the same chamber pressure, this is PC, this is the start of the nozzle, and in the second case it starts from PC but continues further till I get a much lower value of, let us say, PE2 over here. Now supposing I consider a situation wherein the ambient pressure is somewhere over here. Let me replot this. What I am trying to tell you is, the pressure is varying along the nozzle. Supposing the ambient pressure distance along the nozzle and this is the ambient value of pressure PA, which is the value of the ambient pressure. And now in the first case the rocket nozzle is small, it comes over here. In the second case the rocket nozzle is bigger, and therefore maybe I expand it out still further, it comes over here. The first case is PE1, the second case is PE2. Therefore in the first case what is going to happen? The pressure at the exit is greater than the ambient pressure. In the second case the pressure at the exit, that is PE2, is less than the ambient pressure, and this is what this graph tells you. Pressure at the exit for the first nozzle, which is small, is higher than the ambient pressure. Pressure at the exit is less than PA. Therefore what is it I have done in the first case? The expansion is not completed. Therefore I call this nozzle as under expanded nozzle. It is not. In the second case I expand it over and above the ambient pressure, therefore I call this particular nozzle as over expanded nozzle. Right? Are there any defects in this? What have I done when the nozzle is small, the expansion is less? What happens? I am not able to get a high jet velocity because my exit pressure has still not been able to match the ambient value. That means I could have got much more had I really expanded it a little bit more, come over here, or rather it would have been good for me had I expanded the nozzle something like here till the time the pressure matched over here. What is the problem with over expanded nozzle? Well, the pressure here itself is equal to the ambient pressure. The ambient pressure is now, that means the pressure is going to decrease, and if it is going to decrease, it is just not possible. Mind you, the flow here is supersonic, it does not know the conditions what is existing over here. All of a sudden the supersonic flow finds a higher pressure because it has already been expanded to a lower pressure, and therefore it is necessary that something like a shock stands over here. That means I have supersonic flow, it is not able to see anything before it, but all of a sudden when the flow reaches, it sees a higher pressure, and therefore something like a shock is required to match the exit pressure. And what would happen? Let us plot it now. What is going to happen? I have something like this, I have a nozzle here, right, and now the pressure has come to the ambient over here, and therefore if I were to plot the pressure is going to decrease, I should have a shock wave, and the flow downstream of the shock wave is sonic, and therefore it will take me back to the ambient pressure. That means there is going to be a shock, and with shock the flow is going to separate out. If it is going to separate out, I have a region of higher pressure, and since I have higher pressure here, the performance of this nozzle may be even better had flow not separated. But normally this flow separation does never happen symmetrically, and it leads to something like side forces, and therefore over expansion is not preferred at all. I will get back to this point. This point will not be clear at this point in time. All what I am trying to say is, well, if my nozzle area ratio epsilon is not properly tailored and I get PE which is greater than PA, I have under expanded nozzle, in which case my nozzle performance is poor, I do not get the high value of Vj. But in case my PE is less than PA, I will have something like a shock, I have something like a flow separation taking place in the nozzle, and if I consider a section of the nozzle, that means I have this, I consider somewhere over here flow separation taking place. Flow separation does not take place uniformly, with the result at some place I have higher pressure where flow separation takes place, somewhere flow is not separating low pressure, and therefore high pressure will give me higher force, and the rocket in that case will see something like a side force but because of the higher pressure on the nozzle, and this is again not desirable. We will come back to this, but after seeing a few pictures on flow separation in nozzles, what do we really mean? Let us go back and ask ourselves, can I make a plot of flow separation, or let us say an under expanded nozzle? How does the flow take place? Let us consider this diagram, a chamber, a nozzle, now what is it we are telling? This is the center line. We tell ourselves for the under expanded nozzle PE is greater than PA, therefore when the flow comes here it meets a lower pressure, therefore I have something like flow is going to expand out like this. And how does the flow expand out? I have rarefaction fans which are generated, Prandtl-Meyer expansion at a point, and similarly over here, that means the plume comes here, this is the low pressure region, this is the higher value of pressure, and when the flow expands out, I have here the back pressure which is the ambient pressure is equal to PE, and then the flow, these are the expansion waves which are coming over here. Similarly over here again on the other side, I have the same expansion fans coming over here. Why do we need these things? Because at the center the flow velocity is still higher, therefore what is happening here, the pressure has been matched, but here I have expansion, therefore here the pressure is going to be less than the value of PA, that is the nozzle, that is the flow pressure here is going to be less than PA, and when this rarefaction fan touches the boundary of the plume, you get compression waves coming like this, and they form a compression wave like this. Similarly, I get all these things forming compression waves and a net compression wave coming over here. I have compression region over here, and therefore, now because of compression my pressure becomes greater than the ambient pressure, but on the outside the effect of this is to still give me the same value, and these compression waves travel still forward. This is the boundary of the plume, and when a compression wave or a oblique wave strikes an interface, I start generating rarefaction fan again. That means I start generating rarefaction fan again. Over here it strikes, I start generating these rarefaction fans again, and then this comes and strikes here. I again get an oblique shock wave. This strikes the plume over here. I again get oblique shock wave, and this is my shock wave, and this type of thing continues. In other words, I have something like an expansion fan. I have a region of low pressure, then I have oblique shock waves, and these oblique shock waves give me higher pressure. Again I have smaller region, and again high pressure region, and this continues. In other words, I have regions wherein pressure is higher, and whenever pressure is higher the temperature is higher. If temperature is higher, the flame becomes sort of more luminous. When temperature is higher, you can see something because it becomes more luminous. We find that because of under expansion there is further sudden expansion, that means there is an expansion fan, and this expansion fan impinges on the plume surface, and when the expansion fan impinges on the plume surface, the expansion is reflected as a compression, that means as weak oblique shocks. These oblique shocks further compress the medium. The interaction of the compression waves with the plume surface forms expansion waves, and the process of compression and expansion continues. If I have an over expanded case, and let us just put that down also such that we understand the wave pattern. It is a little bigger nozzle. Now I have PE which is less than PA. What is going to happen? Much earlier I am going to get a shock which is going to make the pressure over here higher, because supersonic flow I need a shock which will match the higher value of pressure. Therefore, what is going to happen is the boundary will come down like this. I have a shock wave, it interacts with the boundary, and what happens is when it interacts with the boundary I get expansion fans being thrown off, and the plume expands over here, and similarly over here let us plot the center line again. You are getting it is thrown off over here, thrown off here, thrown off here, this continues over here. These again, the rarefaction fan interacting with the boundary forms an oblique shock. Similarly over here they form something like an oblique shock over here. And then this oblique shock interacts with the boundary here. Again you have rarefaction fans, and the process continues. In other words, in one case I get a higher pressure region little bit away from the nozzle exit, in other case I get a high pressure region just at the nozzle exit. That means over here I get a high pressure region because I have oblique shock waves which create a higher pressure region, and I get wave pattern something like this. To be able to appreciate this point, I just took some pictures which are of some of the nozzles, and this will become clear to you now. See, this shows a particular second stage of PSLV, and here you see this is the divergent portion of the nozzle which is conical nozzle. This is the combustion chamber, and if I take the inside configuration of the nozzle, it will have a throat and it will come back like this to the chamber. Therefore, I am looking at the outer portion of the nozzle here. When the nozzle fires for some time, the nozzle becomes red hot. Maybe we are looking at this part, it becomes red hot because it is hot gases, and when hot gases are flowing, this is something like an overexpanded nozzle. You see the white flame or plume over here, you find something like this oblique shock which stands over here, and downstream is not clear because they spray water and stuff like that. Let me go to the next one. I show this again. The conical nozzle is shown by the red color because it is white, it is hot. The white part is the hot gases which are going out. You find that there is something like a oblique shock over here, it interacts along the base, and subsequently some events are going to happen. Let us go to some other experimental firing. You know, this shows another engine test wherein this is the exit of the nozzle, and in this particular case the exit of the nozzle is such that the flow is probably overexpanded, and therefore you have something like shock waves which are coming, and what happens is the high pressure region over here gives you a higher pressure and higher temperature. Therefore, I have oblique shocks like this which give me a high temperature region. It looks like a shock diamond, you know, I have a high pressure region which is luminous. Afterwards the oblique shock comes here, I have rarefaction fans coming, another oblique shock coming, I have another white patch over here, again the process, I have something like a series of shock diamonds which are coming. That is because at some places the flame is more luminous. I just continue with this. It shows SR71 which is a plane. I see the shock diamonds over here in this particular case, and we continue with this. This is a test of an engine, and here you find there is a shock here and something like this. This is because the exit condition is either underexpanded or overexpanded. We will continue with this in the next class. I will just review this again, and we will continue with what are the other things we have to do in the nozzle. Thank you then.